Good afternoon, my name is Marco Antonio Paredes. I am a PhD candidate in material science. It's a pleasure to share with you the topic Tridimensional Analysis of Porosity, derived from LPBF's additive manufacturing by computed tomography, and I would like to talk about the introduction. The laser powder bed fusion LPBF is one of the most versatile metal AM techniques. In this process, the laser melts a metal powder, followed by solidification of the melt to form the final product. The steels, such as 1.2709, are primarily used for manufacturing tools and molds since they are characterized by a high hardness combined with a high ductility. Their specific mechanical properties allow, allow use high stress components due to its high wear resistance. However, the porosity is one of the main challenges in the LPBF process and has a considerable impact upon fatigue profiles of a bulk. The porosity can be usually introduced by almost all AM process parameters. In order to prevent a failure, it is important to be able to determine the position, direction, shape, and size on the porous to know the final density of the piece of was printed. The CT with cone beam geometry has been used for non-destructive inspection of material science since 1980. The CT offers a 3D imaging inspection in comparison to previous techniques that are limited to B-dimensional results. The aim of this work is to analyze the porosity distribution with samples of 1.2709 printed parts by means of CT. In that sense, the samples at printed condition AP and heat-treated condition HT were analyzed in order to find porosities and internal defects through their finite volume. Then, determined the influence of Hg in the size and distribution of porosities. Finally, the samples were observed using a metallographic optic microscope. Now, I would like to talk about the process. 1.709 stainless steel was chosen. The LPBF technique was used to obtain a coupons printed at 0 degrees and 90 degrees with dimension of 90 millimeters by 75 millimeters and 3 millimeters. For these coupons, ASTM E8 specimens were manufactured using a wire ED machine. Specimens at 0 degrees and 90 degrees are reserved as they were printed. Other specimens printed at 0 degrees and 90 degrees were subject to solubilized heat treatment at 900 degrees Celsius with a heating rate of 10 degrees per minute and cooled to air. The etching is carried out at 480 degrees Celsius. Subsequently, specimens with heat treatment and without heat treatment of 2 millimeters by 2 millimeters by 2.5 millimeters are cutting off a diamond cutter, which used for characterization by means of CT. A sample of each specimen was cut in order to be metallography prepared, and all samples were observed using an Nikon EPHub 200 metallographic optic microscope. The specimens with heat treatment and without heat treatment are scanned by 0 degrees and 90 degrees using a microtomograph, 160 kilovolts and 80 images with an exposure time of 2 seconds to acquire a volume with a resolution of 2.5 cubic micrometers. From this volume, the porosity analysis is carried on. Results. Figures 2A and 2B show aligned porosity for AP and HT samples printed at 0 degrees. Porosity size and number decrease with the thermal treatment. Elongate porosity becomes spherical. See Figure 4. Similarly, For the 90 degrees test specimen for both condition AP and HT, a significant reduction in porosity is shown in the figures 3E and 3D. In figure 5A and 5B, the lines on martensite within columnar grains are seen in events the tracking along the printed sample, which indicates the printing direction. The figure 5C and 5D reveals the microstructure of the sample after HT condition. There is seen the tracking disappeared in the just elongate grains. See white arrow in the martensite remain. Conclusions: porosity and pore size are reduced due to the heat treatment. The porosity is aligned with respect to the printing direction. The sphericity of the pores and greater when the pore diameter is smaller. The tracking lines reduce as effect of the heat treatment and martensite remain. Thanks a lot, Marco.